Good morning, everyone. I'm Jamie Weaver. I'm an associate director at Janssen Research and Development, formerly of the Epidemiology Analytics Group, but now we have a new name. We're called the Observational Health Data Analytics area. So that's me. And I'd like to introduce my other faculty members here. This is Martijn Schumi, and this is Alex Rekas. And then Patrick Ryan will be popping in and out as the day goes on. It might be a little painfully slow, but before we get started, how about we all go around the room and introduce ourselves? Could we do that? There's some interactive components of this day later where you'll be working and collaborating with other people in the room. So maybe if we could just say hello to everybody right now. Could we go around and start with you and just introduce yourself, 2 seconds on your background, and go from there?
Yeah, my name is Scott Duvall. I work with the Department of Veterans Affairs, based here in D.C., but live in Salt Lake City, and I love informatics and data. Good morning, everyone. My name is Cohort. I'm a clinician by training. I came from Seoul National University. I'm a newbie to this field. Recently, I received 2 government grants where I have to use, or I was forced to use CV-based analysis. So that's why I'm here. So see you.
Thank you.
Hi everyone, my name is Faith Parsons. I work with CareSet. We're a startup company. We're the first company who has had 100% Medicare access. So we support a lot of pharma companies and drug releases in population identification for clinical trials. I'm new to OHDSI and overall, but I'm here I'm exploring whether we should proceed with using OMOP, and I'm also interested in how other people are using it through the
You're in the right place.
Good morning, I'm Paul Hill. I'm a data analytics consultant for Providence St. Joseph Health, a large integrated health system with just over 50 hospitals on the West Coast, and also a newbie and looking forward to learning more today.
Yes, from the robotic group doing database studies, and new to OHDSI and OMA.
I'm Tommy. I'm a clinical pharmacologist. I'm working at a knowledge and university from the hospital, and at the moment I'm working at the Howard.
My name is Simple. I'm from Chicago. I'm responsible for the community efforts.
I'm Ted from Korea. I'm
I'm looking at Epidemiology. The kind of converting instrument in South Korea. We converted 12 hospitals now. So we want to know about more like city now. In China.
My name is Kaya. I'm working for Epidemiology in Korea. I'm data analysis. So I'm trying to use analysis in city areas. So
Who's this guy in the back?
I'm not really here.
Okay.
Hi, I'm Martin.
Somebody? Yes, sure.
Hi everyone, my name is Hwang Mo-ya. I'm from South Korea. I'm working for the Samsung Medical Center, and I study common data model and implementing. Thank you.
I'm Phil. I'm from it's called Epidemiology, and we are basically software.
Hi, I'm Mark Kruger. I'm from Sanofi. I have a data management and analytics team there.
I'm
engineer program at the University of South Korea also. And my background is political, but currently also studying medical informatics under Professor Park. And I've been attending PI working group for several times, but even though it's not been held for several weeks, but yeah, I'm interested in population level estimation, so I want to learn more deeper. So that's why I'm here. Thank you very much.
I'm Young Park from South Korea, and I'm a family physician, and I'm working at National Insurance Service hospital where we have 1 million patients CPM data.
Great.
Hi, I'm Amy Davis. I'm a data scientist with PSAC based at the Children's Hospital.
Hi everyone, my name is David Wang. I work on the real world evidence analytics team in Louisiana. So we just started in the process of converting training data to form of common data model. And I would like to learn more develop tools provided by Audit. So thank you. Thank you.
Hi, everybody. I'm Mitch Conover. I just started last month at Janssen Research and Development. I'm working in their Epidemiology group. And before that, I was working on the academic side at the University of North Carolina, mostly methods research with causal inference in large databases. So in my new job, I'll interact very heavily with the OHDSI tools.
Great, thank you, everybody. Sounds like there's a variety of backgrounds here, and many people like dipping their feet in the CDM pool for the first time. So that's great. So how many people here have some background in causal inference methods using observational data? Okay. All right, so that's what we're going to be talking about. This is a tutorial on how to do that using the tools developed by the OHDSI community. So like our agenda today is here. As you can see, we're going to talk about an overview of the new user cohort method design, and that uses large-scale propensity scores to and outcome models. Following that, Patrick will come in and we'll brainstorm on coming up with our own research question. And this will be a hands-on exercise where everybody will come up with a question that's of some clinical importance, and then we'll discuss and decide on which one we will do together. We'll have a short break. Following that, Martijn will lead us through how we dissect a published cohort study, and we will assess all of the decisions that have been made in order to get to the point where you can get an estimate that is intended to show a causal effect. Alex will follow this with all of the threats to the validity of study results, all of the things that can go wrong when trying to identify causal and make causal inferences from observational data. And then I will walk everybody through the UI that is in the OHDSI tool called Atlas for completely specifying a new user cohort design study. And in this like really handy tool, you can point and click your way through all of the decisions that are required to fully specify one of these studies. And of course, under the hood, this is creating code that will actually execute the thing. Then we'll have a break, and then lastly, we'll collaborate together on the design of the study that we've decided on. And we will go through and actually specify this together. So yeah, this is the title, Overview of the New User Cohort Method. So OHDSI's mission, we spoke a lot about this yesterday. It's to improve health by empowering a community to collaborate, generate evidence that promotes better health. And we're going to do something like that today. Yesterday, as you saw, there were a whole variety of OHDSI activities on display. And I like to think of, personally, I like to think of what OHDSI does in this like simple, like admittedly oversimplified matrix, but it's a nice way to think about the various tasks that are being done. There's a clinical characterization for doing things like disease natural history and estimating the frequency of occurrence of something or quality improvement. There's population level effect estimation, which is what we're doing now, and this is a use case for like safety surveillance or comparative effectiveness. And prediction is, of course, for like precision medicine and disease interception. And then all of these three like use cases rely heavily on methodological research, establishing the scientific best practices and evaluating how well these best practices actually perform, and then encoding those and then the open source analytics is about encoding those best practices in software tools to make actually executing these things easy. And then lastly, there's the clinical evidence generation, which is sort of end game of all of this. The point of it all is to generate useful evidence for patients and providers and all of the stakeholders that are involved in this. And so today, we are going to spend our time in this box of the matrix. We're going to use population level effect estimation approach to generate clinical evidence. So there's to start thinking about how to establish causal inference, you can start thinking about something called counterfactuals. Has anyone heard this term before? Counterfactuals, yes, counterfactual reasoning. It's people do this every day in all of the decisions they make, that whether you notice it or not, and people do it. Kids do it long before anyone could have taught them how to do it. Kids just kind of do it. It's like my son does it. I see him. I can see him thinking to himself, had I not pointed over there and shrieked, no one would have brought me that tennis ball. Or you can think of like, had I studied more for that exam, I would have got a better grade. Or had I not gone to that party last night, I wouldn't have this headache. And like these are just really intuitive ways of thinking that we all do. And and just go on with these ridiculous examples. Like my dad says, had I not got that LASIK procedure, my depth perception wouldn't be so screwed up. But anyways, and this is just endless. There are endless examples of it. But it's highly doubtful that like my dog considers this. I don't think my dog thinks about what would have happened if he doesn't bark at the mailman. So it's really it's about like his counterfactual reasoning is about considering what, an outcome under an alternative scenario that didn't happen. And there's always, in thinking about those two scenarios, there's always a decision that's made at a certain point of time about which approach to take, and then you see an outcome or you don't. And so like a pop culture version of this is, you guys recognize Neo from The Matrix? Who's seen this movie? Yes, it's fairly popular, and he's handed a blue and a red pill, and it's like, what do? Do you get the dystopian future with robots, or you're actually it's not a good choice for him, or he gets to sit in his room hacking code forever. And of course, he makes one choice and decides to take, I think it's the red pill that takes him to the actual future, and off he goes. But there's And then during the rest of this movie, of course, he considers what would have happened had he not taken that pill. But we don't actually observe that. We only observe what happens when he does take it. So like in terms of counterfactual reasoning for like one person, we can draw a little picture of it. This is believe it or not, that is an ice hockey player. It's from a Nintendo video game back in the day. But you can think of, we can try to visualize this counterfactual reasoning with these cartoons. So like this horizontal line, we can think of this as time, and it progresses from left to right, and we'll see that like establishing counterfactual reasoning for one person is in fact impossible. So this little person's going along in time, and then Morpheus gives them the choice to take the red or the blue pill. And this hockey player takes the red pill and moves along, and then we see what happens to them. So this person has a good outcome, a little smiley face. But then if we want to establish counterfactual, like this person's counterfactual, the only way to do it is to take them back in time to that decision point, and then make sure they take the other pill and have the other scenario, which is, of course, great if you have a DeLorean, but you don't. So in this case, under the red pill, this person got a smiley face, and under the condition of the blue pill, they got the frowny face. But of course, you can't for one person observe this. And again, the cartoon, you can start thinking about how how in data you would actually you would look at this. You think that decision point, for example, is like a time zero. And you can think of all of the things that happened before that point as a baseline period where you can identify people, and all of the time after that time zero, that decision point, where you actually look for what has happened to a person under one of these conditions. So again, counterfactual reasoning in a population is just the same thing. Instead of one person, you do it with many, and over they go, and then back they go, and frowny face, smiley face, puke. And so what you do, and like under the whole population, is you actually summarize which people took the red pill, which people took the blue pill, and then you sort of enumerate them. And then you similarly would enumerate all of the outcomes under these two scenarios. But again, this is very theoretical because you can't have the same people in both of these groups. So because we can't time travel, we have to come up with like an alternative for seeing what counterfactual outcomes will happen in two groups of people. So instead of studying the same population under both decision options, the red or the blue, you can instead define a larger population in total and randomize folks to either of the treatment options, and then compare the outcomes between them. And doing this, there's a large body of work that shows that establishing average causality in a population is possible, even though you can't do it in an individual. So you end up with a situation that's more like this. You flip some people towards the assigned to one group, and then you flip some people towards the other group. And instead of it being the same people in your two decision options, you end up with these ultimately similar groups in the red and the blue categories. And if you do, it's hard to visualize this with just three little hockey players, but if you have enough people, and if you have a sufficient number of people and you randomize them, you will end up with very, very well-balanced groups, and that are actually exchangeable at baseline. So you've got these two groups of people that you can consider equally likely to have the outcome in the absence of any treatment. So really, these once after randomization, the only difference between these two groups of people on average will be whether they got the blue or the red pill, or whatever the treatment assignment is. But as you know, we spoke a little bit about it yesterday. Patrick covered it a little yesterday. It's like randomization in clinical trials are great, but they cost hundreds of millions of dollars and take 5 to 10 years to do, and sometimes you need the answer yesterday. So it's not exactly, and there are ethical reasons that you can't do clinical trials sometimes, like you can't really, randomize. There are all sorts of vulnerable groups that might not really, and might not be ethically appropriate to include in clinical trials, like maybe people that are pregnant, or there's various examples. So in that case, when you can't randomize, or it's either unethical or infeasible in any way, there is another approximation to do it. In this case, you would define a larger population, and then observe which treatment choices were already made among those people, and then compare outcomes between those groups. And you can do this between people who have made different choices, or you can do it within people at different times. Those are self-controlled designs, and that's another story for another time. But for now, we're going to be talking about observing which choices were made that have already happened in observational data, and then comparing outcomes between those groups. But as we know, they're not randomized. There's a whole slew of trouble that goes along if you simply go ahead and compare the rates of outcomes in these two groups. So this is where comparative cohort studies come in. And there are as many definitions of a comparative cohort study as there are textbooks and papers on the subject. And I'm not going to go through all of it, but there are tons. You might recognize some of these. I think there's the modern epidemiology. Here it is. This is the one many of us have read. Without going into all the details of it, let's try to think about how we think about comparative cohort studies in OHDSI. So in defining those two groups of people, the two groups of people that have ended up in a treatment or a comparator group, based on some criteria that's just not random. We call those two groups cohorts. And like the cohorts have a very explicit definition, that is a set of persons who satisfy a set of 0 or more persons who satisfy one or more inclusion criteria for a duration of time. And so like the inclusion criteria, for example, could be something like new use of drug X among patients 18 years older with at least 365 days of prior observation period and at least 2 diagnoses of some condition. So like that is, and then you would have to also think of a time that they leave the cohort. You could say when they are finished their continuous exposure to that drug. And then there are consequences of having this very, very explicit definition, is that a person can belong to multiple cohorts. One person may belong to the same cohort at multiple different time periods. One person may not belong to the same cohort multiple times during the same time period. And you can have no people in your cohort. And lastly, a cohort cannot be defined simply by codes. By identifying codes in a database is insufficient to actually identify people. There needs to be some sort of logic about how you use those codes to identify people. But before I go on, are there any questions so far? I feel like I'm moving kind of quickly here. Yes. A code set is a set of codes or concepts meant to represent clinical phenomena in a database, but on their own cannot be used to identify people. So like a code set is a list of entities. They're supposed to represent clinical phenomena in a database, but a cohort is people that satisfy some rules, and then you have to use the concept sets to help identify them. So it's like there's a code for type 2 diabetes, for example, is you would have to use that plus we want to look for a code of type 2 diabetes after 2000 for people that have also taken an SGLT2I inhibitor. It's like you need to have a little logic in order to use your code set to find people. So like you can define these cohorts, and you can define cohorts in this really nice way where you start thinking of like an initial event, like something that will initially qualify someone for a cohort. So an example could be the first time they had a knee replacement surgery, for example. And then once you've found all the people who've had a first knee replacement code in their history, you would then look back to make sure that they're older than 40 and have osteoarthritis and no rheumatoid arthritis, for example. And then you would have to define also when a person leaves that cohort. You could say if you had some clinical rationale for saying like when someone is no longer a new knee replacement patient, you could say something like 6 months or whatever your clinical rationale is for it. But it's that exit criteria is also important. Databases are full of cohorts. You can, anything you can dream up is in there. But it's like some of them may represent valid comparisons that we were talking about before, and some of them not. So there are new users of drugs, and there's like overlap between people that have taken drug A and drug B. Maybe people that have taken drug C, there's no overlap between people that have taken drug A and drug B. There's the knee replacement surgery people, they're not users of these others. And you can go on and on and on. This is interesting. Had outcome. In the way of doing these comparative cohort studies using the OHDSI method is that you can actually think of not only the cohorts of people you're trying to compare as cohorts of people, but you can actually think of the outcomes also as a cohort of people. Now, this is radically different than the way I was taught this, and I think the way most people are taught it. You tend to think of, you have exposure cohorts, and then some of those people might have had an outcome. You're just counting within the group of, counting within your exposure cohorts to see who have had outcomes. Whereas this OHDSI approach is more modular. You can think of cohorts as building blocks that go into the comparative cohort method, and the outcome cohort is really no different than the exposure cohorts. And when you have this like modular approach to doing it, it means that you can reuse cohorts and you can systematically apply the same criteria for your cohort definition to multiple studies. And this helps reproducibility and reliability of results. Any questions so far? Okay.
Can I ask a question about that last piece?
Yeah.
So you're saying traditionally, what you do, for example, is create two cohorts, which is new users of device D and persons with surgery E.
Mm-hmm.
And then you define some outcome, and so you really only count the overlapping circle
Yep.
part with had outcome 3.
Why don't I can skip ahead to a really nice slide and then I'll go back. Here we are. So I think this is what you're getting at. So you've got, here's initial target cohort T, and there's initial C, and then there's some overlap between those two. And then after you, then perhaps comparing all of those people is inappropriate because there's overlap between them, or they're apples and oranges, and there are reasons you wouldn't want to do that. So you end up then restricting those initial groups down to these smaller ones, which we've called T prime and C prime, and then there's some overlap between them and this outcome cohort of patients. Does this drawing sort of get at what you're?
Yes, but like the technical implementation, even though it's modular, you get the same result. You're only,
Yes.
in theory, looking at the slice of
Correct.
the C prime and the outcome cohort.
Correct.
But you define, instead of just counting how many are in that C, you define an outcome cohort.
Yep.
So it's modular, so you can systematically use it for all studies.
Mhm.
That's what you do.
Correct. And then the software implementation is what does the subsetting to those that are relevant to your actual study. And it's a way that you can then make reproducible, you have reusable sets of people.
Do you ever do anything like look at the outcome cohort outside of those two to see for confounding or other?
Well, one of the nice methods that was on display yesterday and was mentioned a few times in the talk was using some software called Phevaluator on your outcome cohorts before you use them in a study. So independent of any exposure cohorts that you're interested in, you can use a data-driven method to evaluate the operating characteristics of your outcome definition. And you basically create using a data-driven method rather than the traditional like clinical review approach, you would create what a gold standard is, and then you can take your outcome definition and use the empirically derived gold standard to create your performance metrics, sensitivity, specificity, positive predictive value and stuff. And that's independent. We would do that independently of your exposure cohorts. So that then when you do your study later and you see some, I don't know, sensational result, you can then say, oh, wait, but my outcome definition has very poor performance characteristics, so maybe that's what's giving me the sensational, huge result that might be incorrect. Sorry, just get back to where we were. So here are two cohorts in observational data, and you can see these two columns are different colors because these people don't have the little coin flip in front of them. The people that got the reds happen to all be from this one team of pixelated hockey players, whereas the people that got the blue are all on this other team. So you end up with this cohort summary. You end up all of the people that have had the red and all of the people that have had the blue are different. So you have then this outcome summary under red and outcome summary under blue, but you're not sure, or you can't be sure that what has caused this outcome summary has anything to do at all with the red or the blue assignment. Could be due to something else. There's usually something else involved. And back to this video game, here's the Soviet team and the American team. Anyone remember this? Just me? You're with me. Okay. So this is a really nice paper by Miguel Hernan about using big data to emulate a target trial where you cannot do where you cannot randomize, or you won't randomize, or it's infeasible to randomize and do a trial. You want to use observational data to get as close to that situation as possible. And this is a really intriguing idea. And the idea is that your observational study, you want to do everything that you would in the trial where possible. You would think about what the eligibility criteria are, like who's your target population, who are you interested in. Think about treatment strategies and assignment procedures. That's the tricky one. Like assignment procedures in a trial, of course, is randomization, but it's definitely not otherwise. And you want to think of what a reasonable follow-up period is and what your outcomes are and the causal contrasts of interest and the analysis plan. So I definitely recommend reading this paper about how you can try to emulate this when your goal is to make a causal inference using observational data. You want to try to replicate the tried and true method for doing it. So where it's randomization here, in observational data, an approach to making those populations exchangeable or as close to exchangeable as possible is using something called propensity scores. We're familiar with propensity scores? Everybody? Can I see hands? Yes, yes. Almost everybody. Okay, good. This is the probability of belonging to a target or a comparator cohort given baseline characteristics. And here's the probability of z equals 1 given x, and where z is the treatment assignment and x is the set of all covariates at the time of treatment assignment or beforehand. You can use propensity scores as a sort of balancing score, whereas two cohorts have a similar propensity score distribution. The distribution of covariates should be similar between the two groups, but you should check this. This came from like a Rosenbaum and Rubin paper back in 1983. And the idea is like each patient gets their own propensity score, and those with similar propensity scores are similar on all the characteristics that predict the treatment status, or at least that the observed characteristics that predict treatment status. And the goal is to find treated, or like target group and comparator group, the red and the blue group people that are similar in terms of their propensity scores, but actually have different treatment status. So you end up with this situation where in an observational data set, you've got people exposed to red and people exposed to blue, but you have people that exposed to blue that are similar to those that were exposed to red. And if you can get a large enough, if you've got enough people to start with, you can often find people with similar propensity scores. So once you've generated a propensity score for each of the people in your population, in your two cohorts, you can actually observe how those propensity scores are distributed in this nice density plot. And in this case, are people familiar with this? Have we seen these before? So the idea here is the red pill people are distributed a little to the left by this red dotted line, whereas the blue pill people are distributed a little bit to the right. And the shaded area on the left are patients who have never been treated with the blue drug, and the shaded area on the right are patients that are treated with blue that never are like people treated with the red. And then this area in the middle is the overlap between the two. So you have folks exposed to both the blue and the red pills that have scores that are similar. Pardon me? Yeah, no, I see it. How would you explain that green line?
Also, the point there is that so there was a lot of people in the blue group at that point. And they also have a pretty high probability of being in the blue group, but there are people, a smaller set of people, in the red group that have a similar probability of getting that blue treatment.
Right. Is that lead to something else? Is it like an inflection point where you have an inclusion?
No, it's just not a special point on the
Oh, okay.
graph. It's just saying that
Just point that out. Okay.
within that group, area of overlap, you will find some people that in either group that have the exact same probability.
Oh, yeah. Okay.
And then like where those two, where the red and the blue lines meet, there's the same number of people in the two.
So you mentioned fee evaluator before.
Yep.
Is fee evaluator like a propensity score for outcome, and this is a propensity score for exposure?
Well, they both rely on using predictive models. So the idea for creating a propensity score is you would fit a predictive model, like predict membership in a target cohort versus a comparator cohort, and then whatever the model is that fits that best will provide a propensity score for each person. Fee evaluator also uses predictive models, but for a different purpose. It wants to predict who would have who's likely to have an extra specific version of the outcome relative to people that you're sure don't have the outcome. And then in that, you would use those probabilities. In that case, that's not really a propensity score. It's a predicted probability of having an outcome, but it leverages the same predictive machinery.
And maybe to take it one step further, it creates two groups, the shaded areas that are the super likely to have it versus super likely not to have it, and those become your reference standard that you...
Ish. It's yeah. It's a different application of a predictive model for fee evaluator. But let's talk about that a little later on. It's a really clever application of using predictive models. It's new. Usually in those for those circumstances of validating your outcome, you would lock a bunch of clinical people in a room and say, tell me who does and doesn't have the outcome in these 1,000 people, and then you would use that as a gold standard. But the fee evaluator approach uses a predictive model to ultimately do the same thing. And then whoever has a high probability of having this extra specific version of the outcome, then that's used as a gold standard. So again, different application of a predictive model, but uses the same approach. Can I go on? So here is a nice paper by Glynn and company that gives a couple nice reasons for using propensity scores in pharm epi. And really any observational and comparative cohort study doesn't necessarily have to apply to pharmaceuticals. Like the theoretical advantages are that confounding by indications, the primary threat to validity, to valid estimates, and propensity scores focus directly on indications for use and non-use of products or treatments under study. It's called the propensity scores, the matching or trimming on the basis of propensity scores or weighting on the basis of propensity scores can eliminate uncomparable controls without the assumptions of linear relationships between the propensity score and the outcome. You get better improved estimation with fewer outcomes. It allows matching on one scalar value rather than needing many degrees of freedom if you were to put all of those covariates in a single model. See what I mean? Like if you match on a propensity score, then your outcome model will really just involve comparing two groups for one outcome rather than using a single large model that includes treatment group and then a whole bunch of potentially confounding variables. The propensity score by treatment interactions. It allows the exploration of patient-level heterogeneity in response and propensity score calibration to correct for measurement error. again, it's a good paper worth looking at.
I think you're about to jump into it. I don't know if you're jumping into the next slide, but maybe we can talk after. Like, there are a couple like rules I'm not sure about when implementing propensity score. Like, there's a bunch of different algorithms across softwares. Some are good, some are horrible. And so I don't know if you have like in the final slide recommendations for like, if I use confounding in my propensity score model, do I use it afterward? You know, in the follow-up model, like PS match and SAS has been horrible to me.
Yep.
Like, you know, in this data has been okay. What do you recommend for R Python? So like, how do you implement? Like, what's the recipe?
So I think in terms of the question of what is the best approach to it is an empirical question, and you can what you can do is come up with some metrics for what you consider to be good and bad in terms of what a propensity score is supposed to do, and then evaluate all of these different approaches on it. And I'll plug Martijn and Yushi and Mark's paper that they published recently that took all of these different methods and just compared all of them in terms of covariate, balance, propensity score overlap, and importantly, how well the balanced groups perform when you look at negative control outcomes. And negative control outcome, anyone familiar with negative control outcomes? Yeah, it's the idea that if you're trying to compare the rate of outcome occurrences between balanced groups, between a target and a comparator cohort, there are outcomes that you would expect there to be no different between those groups. Like if you're exposed to two different hypertension drugs, you should expect no difference between the groups afterwards and their incidence of hangnail or like ingrown toenail or like something else, a broken leg, or like, you know, there are all sorts of like negative controls that you can use to actually determine whether you've properly balanced your groups. And if you've balanced well, you'll see no difference between those groups. If you've balanced poorly, you might see things that you wouldn't expect. So what you can do is you can set up like methodological research where you balance groups by all of these different propensity score methods, and then look to see how well they operate on what you would expect to see. And
that's more like a secondary outcome. Like, how do you know? Like, maybe I don't know if my question is like there's a true answer or if it is a measurement answer. Like, if I'm including a confounder to balance a propensity score, like gender, do you include that in the final model to look at your outcome, or is that like depend?
So maybe important to point out that there are I think two schools of thought about propensity models.
Okay.
So there is the one by Ruben and the one that we are in, is that says that the propensity model's only goal is to predict the treatment.
Okay.
And the variables that go in there are the variables that you use to predict treatment. You don't care about the outcome at that point. And there's another school that says the only variables that go into the propensity model are potential confounders.
Okay. Yeah.
But we actually we believe that that's probably not a good idea for several reasons. But so our approach is really to try and predict the treatment. And actually, we have a very simple approach, and that is instead of hand-picking several covariates that you think might be predictive of the treatment, we use a big data approach where we just throw in any variable that we can think of.
Okay.
But I think that's actually going to be discussed later on.
Oh, great. Okay.
So there are various methods for once you've created propensity scores for the people in these groups that you're wishing to compare. There are various ways that you can use your propensity scores. Like one is you can just put your scalar value in your outcome model, but it's not really recommended. But then you can match on your propensity scores, meaning you can find patients that have similar propensity scores and make sure that you're making comparisons between them. You can stratify on the basis of the propensity score, whereas you basically set bounds or set quartiles or quintiles or deciles of your propensity score distribution and then make the comparisons within those strata. Or you can weight your population on the basis of a propensity score. Yep.
So there's a new method I've been reading about called find stratification package do that?
What's the difference between that and matching? It's the same thing. I think the finer you stratify, you're just getting closer to one-to-one match.
It might have 0, I guess. Yeah. Sorry, good question.
I think of matching and stratification sort of on a continuum, and it's just like the finer you stratify, the more closer you're getting to matching. At least that's the way I think about it.
We do have. Sorry.
No, go ahead.
We do have 2 types of matching that we implement, or it's just also on a continuum. So one is one-on-one matching for every person in one group, you just find one person in the other group, and then the other one is what's called variable ratio matching, where for every person in the one group, you find as many people as you can in the other group.
And again, how well each of these perform is something you can evaluate. Like these are empirical questions. Like your population might balance better within a one-to-one matching situation, or some other problem might balance better in a one-to-many matching situation. Or perhaps your sample size is small and you don't want to lose anybody, so stratification might be your better approach then. But there are different reasons you would want to make these different choices. But again, they're all empirically testable approaches. There's people, I'll speak for myself. I learned stratification first, so I used my stratification hammer lots just because I was familiar with it. But again, it's like it might not always be the appropriate way to do it. You can see what is and what isn't. And
which one of these cut off those 2 ends? Matching does, right?
Yeah, you can. So you can trim on the basis of you can trim patients on the basis of your propensity scores. The idea is that patients with very, very large or very, very small propensity scores might exert undue influence on your final analytic, on your final estimates. So if you're worried that a few patients with large or small propensity scores might be the ones driving your answer, you can trim them.
But matching will actually also often achieve the same thing. Could you quickly go back to that plot where we had the 2 distributions?
Yes, matching just keeps the people in the middle because the people that are in the shaded areas here don't actually have a match.
But they also just don't have matching in the strata either. So wouldn't matching and stratification?
Yeah, so it depends on how you define your strata. If you had like 3 strata or something, it could be that you actually have a strata that has a few in one, but mostly in the other. But yeah, you're right. The smaller your strata get, you probably just have strata where there's just people in one group and not the other, and then it actually doesn't contribute to the estimate.
So all of these methods, or at least these 3 methods, are implemented in the software that runs against the common data model, et cetera. So just like a little bit of detail, matching. Just from our toy example of these funny hockey players, like you would find that this medium-sized hockey player that has been exposed to red is similar to this medium-sized hockey player that's been exposed to blue. And then you can find the larger gentleman and then the skinny guys, and you line them all up. And so what happens is the people that are matched are the ones that you retain in your analysis, and then those that aren't do not contribute to it. So this is interesting though, it's because you need to, in doing a matched analysis, you also need to consider that you are now going to produce an estimate that's on a slightly different population than you defined in the first place. So like that's pretty critical when you're trying to make decisions on the basis of an analysis like this. So.
I mean, this is one-to-one matching. I'm not familiar with variable ratio matching. How would that work? Like, you get multiple large people for the same large group, then how do you?
This is definitely too simple to show how that works, but it's like in a one-to-many situation, you would find you would say there's some range of propensity scores like that you will deem acceptable to match a person in your target group. So you say for example, your target person has a propensity score of 0.2, but you say that person is acceptable to match to anybody that has a propensity score of like 0.175 to 0.225. So you've got this this range of acceptable matching scores. So then you would find as many people as possible in that within that matching range to match them. And if there are many, you get many.
Like the optimum, like you might have an optimum top where you have like 5,000 people that match like a 0.2, right? So do you take them all?
Well, you would specify what your maximum like matching ratio is. So you would say something like 1 to maximum 100, for example. Or you could say 1 to maximum 1,000.
But the way that the algorithm works, like really the nuts and bolts, is you first find for everybody in the one group one match in the other group, and then you go back like for the people that remain in the other group. No. So basically, it's a greedy algorithm. So first for everybody you find the best match, and then you go back and then is there another second best match? And actually that dries up pretty quickly, even if the two groups are very different in size.
There's often differences between people, not because there are real differences between people, but just because we have different amounts of information on people.
There's lots of differences because there's unmeasured information on people as well.
So the number of medical facts, so to speak, that a person has, it is covered by propensity scores because they would have a different propensity score.
I mean, it covers the observed medical facts. I don't know if we call it. It's just like the observed information on these patients is covered by the propensity score approach. But that doesn't mean, I mean, a health claim tells you a bunch about a person, but it doesn't tell you everything. And there's the unobserved information that might be driving treatment assignment does not get covered by propensity scores. And that's something that Alex is going to speak about later. So in this matching case, so now we have these people of different colors, but they're at least lined up by their size. Stratification, we spoke about that before, is that you stratify by large, medium, or small. And this way you keep your entire population of people, and you just have these three different comparisons where you've got the large guys up top, the medium guys in the middle, and the small at the bottom. So here we are back to this drawing where you once you use these propensity score methods to either matching or stratify or weighting, you can actually end up changing your cohorts to these subsets of them. So it's like you have your target. Sorry, I didn't actually cover just the language I'm using. Whenever we think about doing these comparative cohort studies, there's just the parlance is to generally think of a target cohort, a comparator, and a comparator cohort. So if I'm talking about T's and C's, that's analogous to the red pill or the blue pill that we were talking about before. So that's why you've got these T's and C's and then T primes and C primes. So like when you would start with a target cohort, you can see in this large circle on the left, you start with this large comparator cohort, the large circle on the left, and there's some overlap between them. After you would fit your propensity score model and generate a score for each person and match on that basis, you will actually end up with a smaller set of those two people. And in this case, it's these smaller circles in the middle we call T prime and C prime. And then once you're comfortable, once you've evaluated whether you think these are comparable groups, balanced groups, exchangeable groups, it's only then where you would start to make comparisons between the rate that an outcome has occurred. Yes?
Just to try and get the spatial aspects with the previous distribution of the propensity scores, the fact that those final analytic cohorts are separated does not mean you're looking at just the non-overlapping parts of the propensity score.
Right. Oh, sorry.
This spatial connection has no relevance to the previous distribution.
Oh, well, no, it does a little bit. So like, for example, these patients here in the middle might be the ones that were out on the tails that again, this
In theory, when you look at that balance plot, that's the blue and the red looking more overlapped.
yeah, the overlapped, yes, the overlapped section are going to be like these patients and then these patients.
So why is the outcome cohort including not only the target cohort, but also, the analytics cohort, but also other
because there could be people in those, after you do your propensity score method, whether it's matching, for example, you could be removing people that have had the outcome, but those are people that are having the outcome that aren't similar to people in your T's and your C's. The idea that the outcome cohort is created independently of the T and the C is like the main drift here. It's like there are people that have had, if their outcome is myocardial infarction, there are all sorts of people that have had myocardial infarction, and it really doesn't depend at all on whether they're in the T or the C. It does for your particular study at hand. You will end up looking for those outcome cohort patients in your T prime and your C prime, but like it's a cohort of people independent of your study.
But the system will only count outcomes that occur after exposure, right? Like there is a time.
Yeah.
Okay.
Yes. Yeah. That's part of the analytic specifications that go into this. Yeah. So here it is. It's like you saw that coming. The analytic outcome cohort. There's the outcome patients in the T and C prime during the time at risk that you specified. And then lastly, it's like the choice of the outcome model is like what defines your research question. So once you've determined which analytic cohorts are the ones you're happy and comfortable comparing, then you need to think about how you're going to look for the outcome occurrence in that case. And there are these are three approaches that involve discrete outcome events. So there's like logistic regression, which is just a binary classifier and determines whether there is or isn't an outcome during a fixed time at risk period. And then there's it gives you an odds ratio, and there are assumptions that are required to be met for each of these approaches. For logistic regression, it's that there's constant probability within a fixed window. The Poisson regression just looks for rates, and that counts how often occurrences happen during a time at risk, and you get a rate ratio. But this requires that the outcome is like Poisson distributed. And then lastly, and it's kind of at least the workhorse in my life, is using a Cox proportional hazards model, which computes the time to event in either of the groups, or time to event or time to censoring. And for that, you get a hazard ratio, but of course it relies on this proportionality assumption. Anyone have any questions? No? Okay. Well, in that case, I think we can ask Patrick to come up here and we can start thinking about how we would design our own study. And the idea with this comparative cohort method is these are the five main inputs that you need to consider and think carefully about when getting one of these studies together.
All right, so, thanks. So the exercise we want to do, so you had no questions for Jamie, so it must be clear exactly how you would define a prediction, an estimation question. Sorry, just jumped to wrong class. Actually, I was just over there going through the exercise of having them define good prediction questions, and at least two of them asked really good estimation questions. So hopefully now we're going to see if we can actually ask good estimation questions. What I'd like for you to do is to think about the fact that we have this framework that Jamie's walked you through to conceptually think about a study, but basically it comes down to you just got to be able to answer 5 questions. And if you can answer these 5 questions, no matter what your study is, if you can answer these 5 questions, then we've got a consistent framework to help you think about the design and implementation of that study. So you need to be able to define your target cohort. Your target cohort is the group that you are interested in trying to estimate some effect for. You have to define a comparator cohort, which is going to be the group that you're going to use as a reference to compare against. You have to define an outcome cohort, being the events that you're going to be looking for. You have to define a time at risk. So what is the horizon of time relative to being in the target or comparator cohort that you're going to be looking for your outcomes? And then as Jamie just went through, you've got to be able to define your model specification. So are you doing a time to event analysis? Are you looking at an incidence rate ratio? Or are you just looking at an odds ratio from a logistic regression? Okay? So what we found is if we can answer these questions appropriately, then we can design a study and run the appropriate set of diagnostics that Martijn will go through a little bit later for figuring out whether or not the data supports answering this type of a question. But if we get confused with answering this, like for example, there's challenges in thinking about, it came up in our phenotype tutorial 2 days ago, questions about like, how do I define non-users? Or how do I actually make sure that I have some comparator that is appropriately comparable? Or how do I actually make sure that I define an outcome that is clearly something that occurs during this time of risk? So what I'd like to have all of you do is think about estimation questions that you might be answering. And if you could take 5 minutes and grab a piece of, I guess maybe write it on the back of your sheet of paper there. Did we pass out the agendas? Oh, we didn't pass them out. We'll pass them out now. So you've got the agenda, and on the back, what I'd like for you to do is actually just fill in these 5 boxes. I want you to think about an estimation question and write down what would be of interest to you. So what clinical question has motivated you to come to this class and learn? Is there, maybe there's a particular exposure that you're interested in learning more about the comparative safety and effectiveness of that exposure. Or maybe you saw that there was some published paper about something that you're interested in. Or maybe you'd like to replicate a trial, because we know we can do that now. Whatever it might be, what I'd like you to do is take 5 minutes and write down an estimation question on this framework. All right, so you guys have spent 5 minutes thinking about a question. Hopefully it's been more than 5 minutes because you maybe came to this class for a reason. You wanted to actually learn about some motivating reason why you came to listen to the class. But I'm interested in what kinds of questions that you guys had and to hear how you've specified your question in this framework. So who'd like to be the first to share their question?
So I'll take a leap. I'm neither an oncologist or clinician nor a statistician or pathologist. But these kinds of questions come up a lot. Advanced non-small cell lung carcinoma, stage 3. Target cohort, those treated with nivolumab, the leading PD-L1 inhibitor, versus those that got standard carboplatin Taxol regimens. My proposed outcome was mortality. I thought about a 3-year window because I thought that would be better just in terms of outcomes, but I know that the drug hasn't been approved that long, so I shaped it back to 2 years, and then just choosing OR as a model.
Very good. That's extremely well done, Paul. Thank you. So let me just write that down. I wanted to hear it, and then, but I'm going to now butcher it because I don't know all those names of those drugs that you just said. But we're doing patients with lung cancer, non-small cell lung cancer, who start. What was the target drug?
Nivo, N-I-V-O for short.
N-I-V-O, which is a
PD-L1
inhibitor. Okay, so it's at the time that they initiate Nivo, these patients who have non-small cell lung cancer, and we're going to compare them to patients who have non-small cell lung cancer who start
sort of standard carboplatin Taxol
Latin Texan. Okay, and the outcome was mortality, and the time at risk was from 1 day to 2 years. So the horizon has a start and an end, but if someone dies the next day, we'd want to count it all the way to 2 years. And you are going to do this as a logistic regression. That is an extremely well specified problem. Well done. That is excellent. So the question here would basically be, we're trying to understand the comparative safety of 2 alternative regimens. We've got groups that we could actually potentially make comparable because they're both have lung cancer. We don't know whether the people who choose Nivo are different than the people who choose the carboplatin therapy. So one of the things we'd want to investigate to do that would be, are those 2 groups actually comparable? And Martijn will walk through the diagnostics that one could use to test that. But then you've got a very clear outcome. There's challenges in many observational data of actually capturing mortality, but certainly mortality is captured in the common data model, and some databases have that well captured. And of course, you have a well-defined time horizon. We're just looking to see who dies in the next 2 years. Extremely well done. Thank you. Who'd else like to share? Yes.
Okay, I'm interested in knowing the additional efficacy by an SGLT2 inhibitor in type 2 in patients with type 2 diabetes who have received metformin and a DPP4 inhibitor for at least 6 months. So the target cohort in my case is going to be patients with type 2 diabetes on metformin plus a DPP4 inhibitor for at least 6 months, and also the comparator, or actually the target cohort has to also receive an SGLT2 inhibitor. So basically, the target cohort will be receiving 3 different anti-diabetic medications. And the comparator cohort in this case is going to be patients with type 2 diabetes on metformin and a DPP4 inhibitor for at least 6 months. And the outcome cohort in this case, I think, is going to be patients with a hemoglobin A1C decrease greater than or equal to 1% point. And the time at risk is going to be 6 months. And in this case, I would apply a Cohorts regression model. Basically, I'm comparing the rate ratio between those 2 groups.
Okay, so let's go through that. Let's see if I can parrot it back. So the target of interest is patients who initiate SGLT2 therapy as an add-on to their metformin and DPP4. So we've got patients with type 2 diabetes who are initiating an SGLT2 as an add-on to prior metformin plus DPP4. Okay. And so this target group makes sense. There are people in the world who have diabetes, who have metformin, who have DPP4, and that's still not working for them. So they go and they make a choice, which is I'm going to add on SGLT2 as my new therapy. So now, following what Weaves was talking about, we have to think about the comparator. So what is this comparator group that is similar to those people who were on metformin and on DPP4, but they don't make the choice of SGLT2? What's the choice that they make?
Well, actually, I just wanted to compare the additional efficacy by an SGLT2 inhibitor in this case. So I thought that the comparator would be patients who have received only 2 medications, metformin plus and a DPP4 inhibitor. In other words, there's no comparison treatment to SGLT2 inhibitors in this case. So I'm not comparing SGLT2 inhibitor to other antidiabetic medications. So no treatment in this case is going to be controlled.
Okay, so this is a great discussion. When we think about that counterfactual, we have to realize that our target group had a moment in time that they made a choice. They made the choice to initiate SGLT2. We often will run into it. I think Martijn will talk about it a little bit later too, but this is probably a good time to dive into this. Yeah. So it's very, very often that the immediate thing that jumps in many of our minds, all of our minds, when we want to do a study is we want the comparator group to be no treatment. And it intellectually makes sense that what we'd like to do is kind of model like what a randomized trial would do. We'd have a placebo group, and we'd like to basically replicate that idea of a placebo, which would be that no treatment. But there's a challenge we face when we're designing observational studies, that we can't define a well-defined cohort at the moment in time that someone had no treatment. Because there is no one moment in time, there's no index date for when you had no treatment, because every moment of your life you've had no treatment if you never got the drug. Okay. And so this actually represents a challenge, because if we think about this proposed comparator group, which is people with metformin and DPP4, well, guess what? Everybody in our target group also belonged to our comparator group at the time before they started their SGLT2.
Can I understand the pre-treatment group as a comparator in this group?
So Martijn will actually go into, as part of his, or is it already in your talk, Weaves? We talk about self-controlled designs?
Yeah, very briefly.
Very brief. So, just for the purpose of the scoping of this class, we're going to be presenting the comparative cohort design, in which case you need two different groups of people that you're trying to model that counterfactual behavior. That is not to say that that's the only way one can do an estimation study. Within the OHDSI toolkit, we've built out methods for self-controlled designs. And so in a self-controlled design, you could absolutely use this same set of people and you could say, what was the events during the time that they weren't on the SGLT2 and what was the events during the time that they were on the SGLT2? A self-controlled case series or a self-controlled cohort design would actually be a tool to answer that question if you don't have a logical comparator, and that would be something that you could explore. In this case, if we wanted to use a comparative cohort design, the main thing that you've got to come up with is how do we define the index date for this comparator group? So it could be that since these people initiated SGLT2, that there's a different set of people who made a different choice at that moment in time. Maybe, for example, they add on a GLP-1 or GLP-2, is that GLP-1, right? A sulfonylurea. So there we go. If we said who initiate a sulfonylurea after having metformin or DPP-4, now we can think about the little hockey players that we've showed you, and now you've got people who are marching forward. They failed, their metformin and their DPP-4 didn't work good enough, so now they hit a fork in the road, and that fork in the road was choose sulfonylurea or choose SGLT2. Now we've got two groups of people that we could potentially make comparable. Your outcome was HbA1c reduction?
Decreased greater or equal to 1 percentage point. So basically, I'm comparing the professionals, right? They do well in those two groups.
All right, cool. So this also represents a challenge with observational data that we need to just be considerate of, because to do that, we need to actually have appropriate capture of hemoglobin before, during, and after treatment. Some data sources might have that, many don't. But also this notion of decrease means that there's some comparison between two measures, because the decrease is in real. And so one of the challenges you have to think about is that given that hemoglobin A1C measurements are happening all the time, how do we decide on which measurement we use as the starting point and which measurement do we use as the end point to create a cohort that would actually satisfy this? So what we could, for example, do is say, find the hemoglobin find a hemoglobin, in the month before they initiated treatments, and then ask, can we see another hemoglobin that was observed in some time window? And then you would take the difference of those kind of things. But there's lots of nuance to that, because of course people get measured for their HbA1c at every single visit. That is an unstable number and it moves around. And so in our data, this represents a real challenge that we would have to be thoughtful in that outcome definition. Your time at risk?
6 months.
6 months, very good. And then the model. So the outcome here is, do you achieve a decrease, yes or no? And the model you were considering was?
Poisson regression.
Poisson regression?
Yeah. So I'm basically comparing two different rates or proportions.
So in this case, it sounds like this is a binary outcome. So someone either has it or not in a defined time window. So in this case, a logistic regression might make good sense because you only care about the difference of those two. You could run a Poisson regression, that would be fine. The case there would be, since this outcome is binary, it just either happens or not. If instead you were to say, like, how often do we achieve hemoglobin reductions, then a Poisson regression would be really ideal in that situation. That's excellent. Good. Who else has got one? Scott.
I really like a study that was done at Indiana University studying the risk of getting a drug-drug interaction prescribed to you.
Okay.
And based on your sex and your age.
Okay.
I'm going to throw this out there and
Okay.
see how
Yep.
well or well. So the T is your female.
Okay. And so the cohort has an index date. So what is the date that we are going to be producing this estimation for? Or was that moment in time?
Yeah, that's a good question. I was going to do that with the TAR, but I was thinking that you'd pick your
So for all of these, we're going to have some moment in time that we're going to look forward to try to observe the outcome. And remember, we're going to use information before that moment in time as our baseline characteristics, for example, to make the groups comparable. And so typically, or in general, what we recommend is when we define a cohort, start by thinking about what is that initial entry event into the cohort? What is that observable event that had to happen so that you start to belong to this population? So if we say women, can we be more specific? Like, is it women who had a outpatient visit on a given moment in time, and that's at the time of their first visit, for example, or at the time they initiate a treatment?
Yeah, but if you say the time of their first visit, does that mean they don't have a baseline because you're indexed?
Or you could say the first visit after a year. Or I'm asking you to tell me what would be the anchor you'd like to use. I can't just take women, because turns out that women tend to be women for lots of moments of their life, not just one moment in time.
How about the first inpatient visit after a year?
First inpatient visit.
Sorry, first outpatient.
Outpatient, okay. So women who have a first outpatient visit after a year of observation. Okay? So that at least is a defined population. And so now we've got women who are at the doctor, and we're going to try to find the counterfactual for these women at the doctor. So what is our counterfactual of being a woman at the doctor? All right. So we've got a man at the doctor. We got a men who have a first outpatient visit. Now, I'm not a clinician or a biologist, but I may need a medical opinion on this, but I'm not positive that this is a perfect counterfactual. But let's keep playing. And what's the outcome that we're interested in? It's observing a drug-drug interaction.
Well, being prescribed.
Being prescribed a drug-drug.
Medications that have an interaction, and so there's 150 on the list, but the one with the biggest relative risk for women is what they found was amitriptyline and fluoxetine.
Okay. So the outcome is getting prescribed a drug-drug interaction. And we'll just use the example of, was it amlodipine? What did you say? Amitriptyline. Amitriptyline plus fluoxetine.
Are they normally prescribed at the same time, or does one start on one and then you have the choice to get the second?
Well, they're prescribed for different reasons, so that's a good question.
Amitriptyline is for what?
Tricyclic.
Yeah, are those both antidepressants?
Yeah, but one's a tricyclic and one's an SNRI.
Yeah, but they are both for depression.
Oh, you're right.
So
That was the example I used.
And so this is good. So let's go back to thinking our counterfactual thing. So maybe the question is, we have depressed patients and who get one of those drugs. And the question is there some sort of causal effect about some intervention that will then cause, is there a difference in some effect that will cause this outcome from it? If this was a prediction question in the other room, I would define this cleanly as amongst people who have depression, amongst people who have depression, who go on to get this harmful drug-drug interaction. And as a prediction question, that would be very well specified, and we'd be able to build a model. And that model may or may not tell us that gender and age go into the prediction question. Here on this side of the wall, we're doing estimation. So now we're trying to ask, what is a causal effect that we're interested in to examine this difference? So I'm going to add depression onto both of these groups, because at least that's going to make these groups kind of similar. And I'm going to also think that maybe instead of using an outpatient visit, we do have a moment in time that there's like a counterfactual activity, which is you get one of these drugs. Okay. So I'm gonna just play with your question a little bit to frame this a little bit. Imagine what if we said this group was those that got amitriptyline, okay, and this group was the group that got fluoxetine. Okay, and I'm going to drop the gender thing for just a second. Now I have new users of amitriptyline, new users of fluoxetine, And we could actually ask the causal question, is it something about these drugs that cause people to then get a drug-drug interaction prescribed to them? That would answer a different question. It would not answer the gender question. It would ask the question, is it something about the drug that causes that to happen? Probably not interesting because we don't probably think it's a pharmacologic effect that is causing this to happen. Are you interested though in the gender effect? You want to know, you want to understand if there's an association just like that somehow.
A lot of what our group does is health equity stuff, so we do gender, race, age, those types of things. And is that something that you could put in a framework like comparative effectiveness study? That was the whole reason I brought up that.
Yeah, no, so it's good. So let's go back to, crossing that out, let's go back to women and men, okay? So let's imagine that we're trying to produce a causal contrast of men and women. In order to be able, so that can be a well-defined problem, but in order to prove that the effect that we're observing is really causal to gender, we have to make sure that these two groups are as similar as possible at the moment of their outpatient visit to be able to examine that. So we could specify this as a well-defined problem. We would be studying the causal effect of gender. I think as Martijn would go through the diagnostics, pretty sure we would fail the diagnostics on this spectacularly, because if I take baseline characteristics of men and baseline characteristics of women, most likely we're going to find that those groups are kind of different from each other, particularly for things like frequency of gynecologic visits may be different between men and women. Rates of testicular cancer might be different between men and women. And so these baseline characteristics that effectively are representing gender would actually be a challenge that we would have to try to figure out how to balance. One could choose to say, well, I can obviously get rid of pathologically gendered covariates, but what about covariates that actually probably do matter, like, well, in this case, depression is related to other things like hypertension or cancer or those kind of things. So if I say hypertension, well, we know that there's actually a differential experience of hypertension amongst men and women. And if we try to balance on that, we're effectively balancing on the gender effect too. And so, this framework for answering causal questions absolutely can be applied to this. But one of the things you discover, and a lot of the health equity work that I see published runs into this challenge, you can find associations, but you really can't make causal claims. And what we're going to be talking about a lot today in the class is like, how do we actually get to that causal statement? And so you could, if what you want to do is run the methods that we're going to show you and just produce an association and not make a causal claim because you would fail the diagnostics, then you could definitely do that. But if you are really trying to actually get down to like, can we make, I guess the thought experiment would be, in order to answer a causal question of gender, you would have to have two groups of people who are identical except for their gender. And it's really hard to imagine how we would actually make those groups that similar.
So to put it frankly though, the fact that you're a woman does not cause it anyway. You'd have multiple things. In theory, it is some clinical observation bias or something that is the cause, and that's why these balances may not.
So that's a good one. So then if we say like what is that causal thing that you want, and it's basically some doctors have some bias in behavior that other doctors don't have. Is that what you're saying?
I mean, if it's men and women, then it's all doctors.
Sure, fair enough.
So yes, but I really like where you were saying. Then you could flip it and have the doctors.
Yeah, so doctors who have bias and doctors who don't have bias, that becomes a causal effect of this that you could actually see. Because it's not the gender that's causing it, it's the bias that's causing it. And so it's useful just to think about what is that actual causal element that you get. Otherwise, yeah, you can produce a lot of associations, but then the question is, what do you do with that association?
Perfect.
Yeah, absolutely. Yes?
My example was very similar to the first one, except that I wasn't comparing two drugs. He's like approving now drugs based on marker denominations, positive or negative. Could you look at markers if they're positive or negative as a causal factor? Like, could you differentiate the two groups between like being like a certain mutation positive or negative?
So let's.
I didn't know.
Yeah.
or overall survival. But, I mean, the way that we're going, it's all about like the selection of one drug or another. What if we just want to compare the performance of like monoclonal antibodies or PD-L1 inhibitors with a cancer patient that has, a disease patient that has one marker mutation and the other one that doesn't?
Yep. No, so to be 100% clear, when we talk about this idea of causal effect and we talk about exposure and outcome, exposure doesn't mean drug. Okay. Exposure generically means exposure to something. So you could be exposed to a genetic variant, and you could have a genetic variant. The thing that we would want to be clear about, though, is there still has to be an index moment in time where something's happening, that we're going to have these two groups. So I think it would be at the time that they're like at the time of diagnosis or something. So patients with stage 4 melanoma, and you have with what was the BRAF positive.
Oh, I don't know, because like along the lines of I was just confused, because along the lines of we were going, we were like always choosing a drug versus another drug. And then when we brought up the gender example, that was kind of like hindered into a different direction because of the selection. So I was like, well, you're kind of bordered with a genetic variant. Does that follow the male-female line, or does that follow the drug? So it's kind of weird, right? It's not really, you're not really self-selecting into a genetic variant. So.
So.
It will be hard to index on the genetic variant. It's like, yes, it's identified at some point, but you haven't before.
So like which does it fall in line with the male-female, or does it fall in line with choosing an SGL2 versus
But the index date is not that you had the mutation. The index date is that you were diagnosed
with cancer, right?
Yeah, and so
I don't know.
Could you? What about Miguel Hernan's thing that we looked at about if you picture the randomized trial, what would exposure and non-exposure look like? Like, what are you assigning? Because you were always born with this genetic variant.
I mean,
like the assignment would be some gene therapy that
right.
removes this
There's
from
like
you.
a little bit of discrimination when it comes to generic variants in clinical trials, and that they self-select. Like for people, they always choose to approve melanoma drugs with BRAF positive, so they like don't even look at those cohorts usually if they're BRAF negative, and then the drugs keep getting approved for BRAF positive patients, and BRAF negative patients are kind of left behind. That's why I was like, well, I'm really interested in studying, like, a drug should be approved regardless of genetic variant. It's like, you're waiting for your drug approval so you can get, insurance to pay for it, and then you're like, well, I'm BRAF negative, now what? Right? Like, I have to go to standard treatment of care because the drug wasn't approved for my genetic care.
So to take what you just said, though, what you're interested in is amongst people who are BRAF negative, does the drug work?
So is that the way to frame it? Is it better to frame it that way? Because it would causally look.
Yeah. So
we still would want to compare it to see like I think FDA would want to know that these work just as well on BRAF positive and BRAF negative. Right?
Yeah. So this is actually a really great conversation because we need to talk about what are we doing a comparison for. Mm-hmm. If we think of that counterfactual, right. A person's born with a genetic variant. Okay. That person has a choice to make in their life, treatment A or treatment B. Okay. Right? That's the fork in the road. I don't get to make a choice of my genetic variant until there's some sort of gene therapy, so I don't actually get to make that choice. Okay. So when we talk about I want to compare the effects of being positive versus being negative, well, Alex is going to talk about heterogeneity of treatment effects. Or no? Alex had a great poster yesterday talking about heterogeneity of treatment effects, and that work really is about if we say that there is an effect of an exposure, is the effect of the exposure consistent across subgroups? And so that consistency question, I think, is where you're going. Okay. But if what we did say is we know that this treatment works for people who are BRAF positive, but we don't know if it works for people who are BRAF negative, then I would say that the causal question we're interested in is actually, it's amongst people who are BRAF negative, and what's the treatment for this melanoma?
Oh, I don't know. Pick anyone.
Okay. Okay. Are there multiple alternatives?
Lots of them. Solberaf, I think right here.
Solberaf, I don't know what that is, but okay. Solberaf.
Nevo was at one point looked at it.
Nevo, okay. So imagine that I'm in a fork in a road here, which is I am a person who is BRAF negative. I have melanoma, but I get to make a choice of Solvarav or Nivo. Now I'm answering a causal question about the effects of these alternative treatments in a population of people who have the BRAF negative. So it isn't going to answer the question, does the genetic variant cause the outcome? Because it's not the genetic variant that causes the outcome. What you're interested in is the effectiveness of an intervention in a population who has that outcome.
Okay, so it's better looking at that.
Yeah. Yep.
I have a question. So if these drugs are not approved for the BRAF negative, how will you even find the population? Or are you getting that drug?
So sometimes they're used off-label, right? The question is how long the drug's been on the market and how often.
Yep.
You could certainly interrogate that.
This is a little bit of a different question, but when you talked about you're born with it, does it matter if it's germline versus somatic mutation? Can you randomize the somatic mutation?
Yeah. So similar to doing the gender things, if what you cared about was the causal effect of the mutation, or whatever that would be, then what you really are trying to do is you're trying to have a group of people who are similar on all characteristics except for that mutation to then be able to observe it. But the issue is like, are you interested in the causal effect of the mutation, or are you interested in the effect of an intervention within a group who has or doesn't have the mutation? Both they're different questions. And generally, like when we make these comparisons, really what we're actually doing is we're just saying, I want to produce estimates in different subgroups, and I'm wondering whether estimates in different subgroups are similar or different. And that's this notion of heterogeneity of treatment effects that Alex presented yesterday.
So if you did the same thing with the genetic mutation, positive or negative, and you did outcome, that could be some causal thing.
Yep. So if you had a bunch of people who were identical in the world except for their genetic variant, and then you looked at some outcome, you might be able to attribute the outcome because of the genetic variant. And insofar as you could assign an index date, make those groups identical in every way that you could except for this variant, then you might be able to attribute whatever you observe to the variant. Okay. All right. We're good. Anybody else wants to volunteer one more question to talk through? Okay. So the reason we do this exercise is because what we've actually found over and over again is the heart. So it used to be before OHDSI, and when Martin and I were doing this work a long time ago, we always thought that the problem was actually the technical implementation of a causal question. Like, how do you actually create the data set and write the code and do all of these things. And in fact, actually now there's a really good textbook on this. But before yesterday, there wasn't even really a good textbook on how to actually implement some of the statistical methods that are theoretically discussed. So like propensity score, for example, as an idea that Martin will go through, you can find dozens and dozens of textbooks that tell you the formulas and write about it. But there's only a handful that actually provide you like working code that you can write in SAS or R to actually go do it. And so we thought a long time ago that the hard part was, well, maybe if we just made a really easy package that can perform population level estimation, that'll make all the problems go away. And actually we were totally wrong, because what we realized is actually the hardest part about doing estimation is specifying the problem correctly. It's nailing this framework and defining your T and your C and your O and making sure that you are clear what is that causal question that you're actually asking. What is that comparison that you're making? The tools that Martin's going to walk you through is going to show you how you can implement that once you've got a good question specified. But if you start with a bad question, it doesn't matter what the software does. What the software will help you with is sometimes you'll have a good question that the data can't support. That's why we have diagnostics that you're going to get to see that will help the data tell you if you have a good question that can't be answered. But what data can't tell you is if you just don't have a good question to begin with. And so the reason we want to go through this exercise is just to help you think about like the most important thing that you'll do in defining any study is actually just defining the problem correctly up front. Paul started us with a really good one here at the start, which was very cleanly following this framework. So we had people with lung cancer who took one treatment, Nivo, versus another treatment, carboplatin, hard outcome and time risk. This is a good question. I don't know whether the data would support this question or not, but it's a good question that's defined well enough that we could attempt to see what would happen. So I'm actually going to, and as we reframed your question, the idea that you have people with type 2 diabetes who now hit the fork in the road and make the choice between SGLT2 and sulfonylurea, that is something that is a well-specified counterfactual moment in time. We don't know whether the data would tell us that we could actually find people that are sufficiently comparable at that time, but we could do that. Yeah. So in the afternoon, do we want to try to do one of these? Okay, so I'm gonna, put it to you guys. I heard multiple of you are interested in the cancer space. So would you guys like to try to see if we could, together as a group, try to define this problem? This, I'm gonna have to go learn about these drugs, but look at lung cancer and compare 2 different treatments in lung cancer? Does that sound like, people, raise your hand if you're interested in that problem. Most people are raising their hand. Okay, all right. So this afternoon when we jump into the exercise, we're gonna take Paul. Paul, you're gonna get to lead author your first OHDSI network study, okay? So we're gonna actually take this and try to think about how we can design and evaluate this together. Awesome.
So seriously, though, I was worried about the requisite data because we plugged in with the oncology working group yesterday and they're really doing phenomenal work. But maybe we can find something, right? I'm worried about the richness of stage 3 NSCLC and all that represented and available public data that can be used. You're worried about mortality. So yeah, I want to be honest about feasibility.
Yeah, so we'll be able to take a look. So actually, the reason why I think this is actually a perfectly reasonable question is a lot of what the oncology working group is worried about actually doesn't play into this. You have drugs that are observable, so those give us hard anchors. We can observe a diagnosis of lung cancer. We can see whether or not we can make these 2 groups similar on the data that we already have. There's a chance that there's data we don't have that might mean the groups are still different. For example, maybe we're going to make these groups as similar as possible on every baseline condition, drug, procedure, measurement, etc., but we don't have staging. And because we don't have staging, it's possible that this group is closer to stage 2 and this group is closer to stage 3. However, think of the plausibility of if I can show that these 2 groups are similar on 10,000 baseline characteristics, what's the chance that they're actually way different on stage? So I think it's a reasonable one to tackle. The mortality, so across the OHDSI network, mortality is inconsistently captured, but some databases do have that. So from that perspective, I like this because I can observe the drug. I don't know how much of the drug I've got in the network, but what we can observe, but it's something we can look for. This is a drug we can go look for. This is an outcome we can go look for. From that perspective, we could successfully design a study together. Whether or not when we ran the feasibility of that design, how many people will get back across the network, that's an empirical question that we could think about how to explore together. Yep.
One thing you said is if they're similar on 10,000 other variables, what's the difference that they're like? What's the likelihood that they're different in stage?
Yep.
Isn't stage kind of orthogonal to most other variables? Isn't it just like?
It might be. Yeah, so I'm not saying, and actually Martin will go into it in his talk about the diagnosis. You cannot make any assertions about an unmeasured confounder and whether or not it's balanced. I'm simply saying that if we do achieve balance on 10,000 variables, we can at least posit that whatever we're going to learn, that what we can learn could have some validity to it. But it's absolutely, if we don't see stage, we will have to say in our paper, or in how we'd write that up, that we don't know the baseline stage of these people and decide what the impact of that would be. Very often in some of the work we've done in our department as it relates to these cancer things, if you don't have stage, but you might have things like, for example, number of prior treatments that you can balance on, and it tends to be that those things are really a good marker for disease severity and those kind of things. So being able to show that you're consistent on prior treatments, the treatment guidelines usually is if you're in this stage, do this thing. So there's pretty good correlation there.
And I don't know this area, but if the T cohort question to ask, or?
So what would happen is if they are really given to very different people, the propensity score is going to just separate the groups and say, this is not really a good comparison. So that's a diagnostic that we would have that could actually help you with that.
Yeah, and the whole framework that the oncology worker seems to be focused on is getting to the level of granularity necessary to do these things robustly in cancer.
Yep.
Yeah, because you're both pointing out the fact that an analogous clinical trial would specify these drugs in a third line of therapy setting after 2 lines have failed, and there's very, very specific criteria around stage inclusion. So we're waving our hands here a little bit, but I think it'll work.
Yep.
Just to try. Cool.
Very good. All right.